About planet formation and Dynamics.
Hey everyone, so I'm Kedron and I'm working with Roman Rafikov at Princeton on planet formation and binary systems, and in particular thinking about the 1 kilometer barrier, planetesimals colliding too violently with one another. So I guess just a quick overview of observed binary planet systems come in 2 flavors. You can have a circumprimary geometry where you have one star and a planet in a tight orbit around that, and then a perturbing companion star far out. Or you can have a circumbinary geometry where you have 2 close stars in the middle and a planet going around those 2, like Tatooine from Star Wars. On both examples, we've observed a number of systems where it seems surprising that these would have formed in situ based on what we understand about planet formation. So for circumbinary systems, something like Kepler 16, it has the 2 stars separated by a few tenths of an AU with a planet within an AU. And the stars have a substantial eccentricity, which you would imagine would stir the planetesimals in the disk. And similarly, for the circumprimary system, something like, say, Gamma Cephei, that has a planet at a few AU with around one of the stars, and then with an eccentric companion star at only 20 AU. Again, you would worry that the perturbations from the companion would inhibit planet formation. So why do I keep harping on eccentricity? It turns out that if you have an eccentric companion, that those secular gravitational perturbations from that will excite planetesimal eccentricity to high levels. So a lot of people imagine that planets form. You have a disk of debris, and there's forms small solid bodies called planetesimals, which collide with one another and eventually stick to become larger bodies. But if they collide at too high of relative velocity, then they smash to smithereens instead of sticking, and you don't get bigger planets. Bigger planetesimals are cores of giant planets. Perhaps not surprisingly, this problem is less severe if you have either circumbinary system and then the planet's trying to form really far out. Then it basically just sees its binary star system as one star. If you go far enough away, you don't really see that it's not a Kepler potential. Or if you're forming around one star, if you go close enough to that star, you can more or less ignore the companion. So it seems plausible that these planets may be formed somewhere else, and we know planet migration can work either inwards or outwards, so perhaps they migrated to their current location. So we're trying to ask the question of where in the disk could these planets have formed, and maybe what disk properties would enable formation in difficult systems. So to do this, we have a model of planetesimal dynamics. There's the obvious why are we even worrying about it is gravitational perturbations from the binary, but it's also the disk, and that affects the planetesimals in 2 ways. One, the disk is maybe 10th of the solar mass, or several percent of the solar mass, so it has a gravitational effect, and it also has gas drag, and that's interesting because it affects planetesimals at different sizes differently. And we noted also that the disk is likely to develop an eccentricity. This plot on the left shows a run of eccentricity with semi-major axis in the simulation of a circumbinary disk by Meshgari. So you find not surprisingly that if you move in to the left towards a smaller semi-major axis, that you end up so towards the central stars in the middle, that you end up with a higher disk eccentricity. So we take the eccentricity of the gas disk into consideration. And maybe seems surprising given that the disk is substantially less massive than the companion star, that the disk gravity is something you have to worry about. But if you're moving far from the central star, then a lot of the disk material is kind of around you, whereas the central binary, if you're in a circumbinary, is kind of concentrated towards the center. So it turns out that it can actually be the dominant gravitational component of the perturbation dominant over the companion star in a lot of the disk, and a lot of the parts of the disk where we assume the planet formation might occur. So for example, if you assume a minimum mass solar nebula, a few percent of the solar mass around Kepler 16, you find at 5 AU that the precession of free eccentricity, so that's one component of the disturbing function, is actually dominant by the disk. The disk dominates by a factor of 10 or so. And interestingly, it also enters with a different sign. So this means if you go closer to the central star, the star's perturbations are going to become more and more important. And since they enter with a different sign, at some point there's going to be 0 precession of free eccentricity, and this will be a secular resonance where the gravity the disk and the central stars will conspire to excite planetesimal eccentricities to very high levels. So on the left, you see a simulation from the same Mechiori paper with and without disk gravity. So with disk gravity is the red points. You see this is the run of eccentricity as a function of semi-major axis. You see that at a particular location in the disk where those precession terms are equal, you have a very high excitation of planetesimal eccentricity. And on the right, we did the same thing with the analytical model of the disk that used in the simulation. So I don't have time in these 10 minutes to give a full description of our dynamical model, but I think more or less all of the basic physics is in the intuition of what happens to small planetesimals and what happens to large planetesimals. So small planetesimals have stopping time short compared with the precession of the free eccentricity. So they are essentially aligned with the disk. So if you have an eccentric disk, the small planetesimals will follow the same streamlines as the disk. The large planetesimals, on the other hand, more or less ignore the disk in terms of their equilibrium eccentricity values, except that their free eccentricity is damped out. So they end up on orbits simply determined by the gravity of the disk and of the binary companion. And so this characteristic eccentricity, then the difference between those eccentricities, it sort of sets a scale for relative eccentricities between planetesimals. This is kind of the relative eccentricity between a very small planetesimal and a very large planetesimal. And why would we care about that? So it turns out that the collision velocity between planetesimals is basically equal to the relative eccentricity times the Keplerian speed. There's a bit of a fudge factor there, depending on where in the orbits they collide. Basic intuition is if you have more eccentric orbits, then the angles at which they cross are going to be steeper, so you're going to have a higher collision speed. But if they're aligned, like the red and blue ones, you can see very well, but the ellipses are basically aligned, then they're going to be moving slowly relative to one another, even if they're moving fast relative to like some guiding circular orbit. So high relative eccentricities between planetesimals lead to high collision velocities. So then putting this all together and working out the details, we can create maps of collision velocity in a particular environment. So this is at 3AU in our putative disk, when the Kepler 16 circumbinary planets form. But you see more or less what you expect. Planets of very unequal sizes, so planets that are planetesimals that are affected differently by the gas drag, will end up having high collision velocities. And then on the 45-degree line, so this is plotted in the space of the size of each collision partner. So the 45-degree line reads through the blue trench that corresponds to planetesimals of the same size. And since they're affected the same by the gravity and the same by the gas disk, you find that they end up on the same orbit. So even though they are on eccentric orbits with one another, they collide at low velocities because it's basically the same eccentric orbit. I see them running out of time, so I'll just say that we have a prescription for collisional outcome, as you might expect, and more rapidly. The faster collision leads to a worse outcome. Then we can draw lines on this corresponding to catastrophic disruption. So you see that you get catastrophic disruption when you have similar sized planetesimals colliding at fairly high speed. So yeah, you have the highest speeds in the bottom right and the top left, and that's very different sized planetesimals, but you don't get catastrophic disruption from that just because you collide a very small thing into a big body. It's not going to completely destroy it. So then we ask the question, in a particular environment, do we or do we not get catastrophic disruption? So let's look at the middle plot. This is for Gamma Cephei. This is one of the systems that seems surprising that you could form planets in. So it says in the plot in the space of disk mass on the x-axis and disk eccentricity on the y-axis. And the gray region encloses regions in this space where there is not catastrophic disruption. That's where it seems reasonable that you could form planets through collisional agglomeration of small bodies. What we find is maybe not surprisingly, but not totally obvious, that it requires a massive low eccentricity disk. They basically want a massive disk in order that the disk gravity can be very dominant over the gravity from the binary companion at the location that we observe the planet, and you want a low eccentricity disk because then both the small planets and the larger planets will be on nearly circular orbits, so there'll be a low relative eccentricity between them. And we can do the same sort of thing for a circumbinary disk. Here, the color corresponds to the minimum size above which you don't get catastrophic disruption for that size of planetesimal. And then this is assuming an axisymmetric disk in the space of disk surface density at 1A is basically a proxy for disk mass and semi-major axis. We see in the circumbinary environment, not surprisingly far away from the central stars, you can for planets starting from arbitrarily small planetesimals, whereas close in, for example, the horizontal red line is the current location of Kepler 16. You would need to start with kilometer to several kilometer-sized planetesimals, depending on the disk density. And I'm gathering over saying my welcome, so I'll put the slide up and take questions.
As time goes on and the disk starts to deplete, would that circular resonance sweep outwards?
Yes.
Thought about what that rate?
Well, you know, sweep in the circumbinary system, it would sweep outwards. In the circumprimary system, it would sweep inwards. So one would hope that if you form planetesimals far up, by the time it sweeps out, the planetesimals are large enough that they'll survive rapid collisions. And one of the things that didn't get a chance to show is that this critical speed for catastrophic disruption depends on the planetesimal size. So you kind of have a weak size around 1 kilometer where they're not big enough to be held together by gravity, but they're too big to be held together very well by strength. That's why it's called the 1 kilometer barrier. So you hope that you form big ones that have high critical speed for catastrophic disruption before that happens.
Your models for these catastrophic and different types of collisions, making predictions for like the grain size distribution and the spectral index that you might intend in the disk?
Oh, in terms of what you would see for micron or millimeter size
Yes.
grains? No, unless you understand a lot more than I do about what kind of dust comes out of collisions from kilometer-sized bodies.
So when you calculate the relative velocities between the kilometer-sized particle, so you normally take the gas drag, considering what is the time scale for that to cross the largest eddy for that particular particles, right?
Sorry?
So you normally take into account the eddy crossing time scale for the kilometer-sized bodies.
So we're assuming for the gas drag that the gas follows just eccentric streamlines in the disk, and then a quadratic gas law.
So do you think when for the kilometer-sized particle is in the regime of the streaming instability and your particles will start then governing the gas dynamics of the system and that can change the laws?
So I think of the streaming instability as taking place for bodies where the stopping time is equal to an orbital time, which I think usually turns out to be centimeters to meters sizes. So yeah, streaming instability provides kind of an alternate pathway to making large planetesimals, which we are not considering in this work. Whereas kilometer-sized bodies have stopping times more comparable to a precession time. So I don't think they couple well enough to the gas for the streaming instability to work there.
I think we have to move on. Thanks.
Okay.